Okay, good afternoon. Dr. Jensen here. We're going to look at a few gas problems. These particular ones deal with finding things like partial pressure. Okay, there's a variety of these kinds of problems that are generally seen in most introductory gas chapters, and we'll look at a couple varieties of what these tend to look like. All right, so let's look at this first problem here. Here we're told that there is a mixture of nitrogen, oxygen, and helium. They give us the individual values that are really the partial pressures. They don't describe them as partial pressures. They simply say that there is a sample of nitrogen, that this mixture has nitrogen at 325 torr, oxygen at 124 torr, and helium at 209 torr. And so they want us to find the total pressure, and they want to know the mass of each gas in the mixture if our sample size is 1.05 liters at 25 degrees C. Okay, so all of this is given in the problem. And this is kind of where some of these problems tend to be a little bit complicated, is that they give you a lot of stuff. They can be a lot of these various values in here that we have to deal with. Okay, so in general, there are a couple of equations that that'll come into play here. The first being that the sum of all the partial pressures adds up to the total pressure of a system. Okay, so if we're looking for the total pressure here, this value is obtained via adding up all of our partial pressures. Okay, so in this case, we have the partial pressure of nitrogen plus the partial pressure of oxygen plus the partial pressure of helium will equal the total pressure of the system. Okay, so we have right? So if we sum up all of our values here, we have a total pressure of 658 torr. Generally in these problems though, as I said in previous videos, when in a lot of the gas chapters, they use a variety of units that are not really the units that usually they're trying to get to. Usually we're trying to work things in ATM or atmospheres, and so they give us these random units to start with in the expectation that we ultimately have to convert them. All right, so if we are therefore then converting this to ATM, so there are 760 torr in one ATM, and so really our total pressure right is 0.866 ATM, okay, or atmospheres. All right. Now, we have the we have the partial pressure values given of each one of these. So there is a separate kind of relationship value here that we can look at for the next part here. Okay, so this is often seen. There's a whole bunch of these derivations that are usually given in gas law chapters, but you have things like you usually have these relationships here, okay, where the total pressure and the partial pressure of a gas are related to the number of moles and the total moles in the system, okay, which should be somewhat intuitive, because if you have more moles, your total moles in the system Okay, if there's 100 moles in the system, if you have more moles of A, you're also going to get more partial pressure resulting from the more moles of that particular gas, right? So in most of these situations then, really what we need to get some information about the moles, right? So this is another example where in some of these practice problems or in some of the problems that deal with the gas law chapters, there's more than one way to solve some of these problems, okay? You don't necessarily strictly have to go this particular way. You could, I mean, in a lot of these are really derivations of the ideal gas law, right? So we have the ideal gas law. So theoretically, we could do the ideal gas law just 3 different times, right? So there's 3, you have the partial pressure. Okay. So if we have the partial pressure of each gas, which we do, we have the volume of each one. We want to know the mass, which fundamentally we need to know the moles of each one. So this is just either one of these is going to give us this value, right? So we need to know this value in order to convert to mass, right? Using the molecular weight, right? So we have to use the molecular weight to convert to mass anyway. Okay, so it's a matter of how do we go about getting the moles of the individual gases. Okay, so either you're going to run this one basically 3 times, or you're going to run this one basically 3 times. Okay, again, it doesn't really save you much. I mean, if we're, this is kind of one of these things where it's not really about which one is faster or better. They both give you the same answer, and doesn't really matter whether it's more or less work. It doesn't really save you much time one way or the other. It's just a matter of which relationship you are likely to understand or recognize that you need to use right away. Okay, so I'm going to go ahead and solve using this first one. Okay, but in order to solve that, I need to know what is the total moles of my system. Okay, so I have we have the equation, we have the similar gas law equation. So my total pressure, I already know, is right, and my volume, I was already told, is 1.05 liters, right? So R is a gas constant, so I'm just going to write the R value, but we have that value, and the temperature here is 298. Okay, so this is plus 273 equals 298 Kelvin, right? So just rearranging terms here. So this is just multiply and then dividing these values over. So the total moles in the system here equal 0.0372. Okay, so now functionally you can take each one of these. Okay, so the partial pressure for all right, so again, I took both of these, all of these, and I converted them into ATM. Okay, so let's do that step here real quick so we can say, so if you have 325 torr, right, there's 760 torr and 1 ATM. So this gives you 0.428 ATM. Okay, so repeating the same process here, I have nitrogen is 0.428. Oxygen is 0.163 ATM, and the helium is 0.275 ATM. Okay, so this is the partial pressures of each one of those converted to to just ATM. Okay. All right, so let me set up my, use this and kind of move this over here. All right, so I'm setting up my equation. All right, so for nitrogen then, the partial pressure of the nitrogen over the total pressure given, or the total pressure we calculated here was 0.866. So this is going to equal the moles of nitrogen over my total moles, which we calculated were 0.0372. Okay, multiply and divide, and the moles of nitrogen equal 0.0184. Okay, I'll do one more here, and then I'll bring all these back together here for the oxygen. Okay, if we're doing the oxygen, you have 0.163. All right, same setup. The partial pressure of the oxygen, given essentially. The total pressure, which calculated, equals the moles of oxygen over the total moles, which we calculated. And so the moles of oxygen equal 0.007. Okay. Lastly, the helium, 0.275. Okay, and then really our last step here for finding the mass. So the 0.0184 moles of nitrogen. Okay. In 1 mole, there's 28 grams. This is the molecular weight. Right, so each one taking the moles that we calculated. Multiplying by its molecular weight. To find its mass. Okay. Like I said, these are long. These can be long problems. Generally, when I do this for my tests, the tests are not this. The test questions are not exclusively this complicated. Generally, if we're looking at a specific kind of test question, it may just ask, individually, what is the total pressure? What is the mass of one of these? What is the mass of helium in this problem? So if you did this just for helium, obviously that demonstrates that you understand how that is done. Okay, so let's look at a second problem here. So this one here is very common in how a lot of these gas problems are presented, especially if we're looking at things like partial pressure. Here we're given, it's simply with two gases, okay, but we're told how much mass there is in two gases within a container at a certain temperature, okay? So if this is a class that has nitrogen and oxygen in it, okay, we know the volume here is the 1.55 liters. Obviously, the gases take up the entire canister, and both of them are at 18 degrees C, right? So everything is the same for the two gases, okay? So their total volume is the same because they're going to occupy all of the space in the container together. They're not like just sitting down here at the bottom like a solid, okay? They're going to occupy the whole container, and they're both roughly going to be at the same, they're both going to be at the same temperature. We're probably not likely to see temperature variations like at the top versus the bottom, right? So here we want to find the mole fractions and the partial pressure. Okay, so mole fraction of nitrogen and the mole fraction of oxygen, and the partial pressure of nitrogen and the partial pressure of oxygen. Again, for test questions, sometimes depending on how complicated the test questions generally tend to be, they are generally, if you find one of them, that's generally what most test questions are looking for, is for you to give the mole fraction and the partial pressure of one of them, because obviously if you can demonstrate that you can find one, then you would just be it's just making the problem longer to find two. So it's, you're not changing, the method doesn't change from one to another. Okay, so we're told the mass of both of these in the problem. All right. So what we want to do is just find out how many moles of both of them are present. Okay, divided by the molecular weight. Right? So just like in the previous problem, the number of moles is necessary, especially if we're coming up with mole fraction, right? So the total moles in the system, so the total moles in the system equal the sum of all of the individual moles. Okay, so this, in this case, the moles of the oxygen plus the moles of the nitrogen would equal the total moles. Obviously, I just swapped those two. I didn't put them in the right order here. All right. So in any case, my total moles okay, 0.0712 is my total moles of my system. So the mole fraction of nitrogen would equal the moles of nitrogen over the total moles. So my nitrogen moles, 0.0 over my total moles tells me my mole fraction is 0.626. Okay. Now, obviously, you could repeat this same process for the oxygen. Also, the mole fractions add up to 100, right? If I only have 2 gases in a system, 100% of those gases would be those 2 gases, right? So if you add up all the stuff, they add up to the total. So you could just plug that in for the nitrogen and solve for the oxygen this way. So we would say the mole fraction of oxygen okay. So 0.374 and 0.626. Okay, so those are the mole fractions. Finding the total pressure, or finding the partial pressures of these in the system. Okay, again, there's more than one way to solve some of these problems. Again, if we're looking at this, the partial pressure of nitrogen, we can use the ideal gas law, another equation that shows up in this chapter. Would be something like this, where the partial pressure of the nitrogen equals the mole fraction of nitrogen times the total pressure. Okay. Now, obviously, you have everything you need here to just keep jamming these into the ideal gas law. Oftentimes, the problems are not this. They sometimes will tell you what the total pressure of the gas is in the system. In this case, we can calculate it. So so we already know that our volume is 1.55 liters. We already know our total moles in our system. R is a constant, and it was 18 degrees C, so that's 291 Kelvin. Okay. So in this case, it's just a little rearrangement. So my total pressure in my system is that. So now I have, functionally, I have my total pressure. I have the mole fraction of each. And so then I can calculate what is the partial pressure of each one. So the partial pressure for nitrogen equals, okay, that we just calculated this one, the mole fraction times 1.097. So the partial pressure for nitrogen is 0.687 atm. Same kind of thing here. You don't have to do this way. You could just subtract this from 1 because the total, or subtract this from your total pressure, right? Because they both have to add up to that. So if this is 0.6, then this has to be the remaining, or you can do it this way by plugging the mole fractions in. Right, so you get the partial pressures of both and the mole fractions of both. So it is not uncommon that these are simply looking for mole fractions for one, and partial pressures for 1 rather than looking for all of these. Again, these are end of the chapter problems. And so the end of the chapter problems usually in most books are generally slightly more complicated than at least what I would usually ask on a test, because if you can demonstrate that you understand how it works, then you don't really need to do it. You don't need to put 3 gases or 4 gases in a system for you to demonstrate how it is. It just takes more time to calculate. Okay. All right. So this last one here deals with gas collection over water. Now we deal with things like vapor pressure of water in this chapter, because anytime we collect gas over water, we have water vapor being present. And so it adds a mixture. It creates a mixture. Even if you're collecting just hydrogen, you automatically have a mixture of hydrogen and oxygen in a system. Okay. But we know now in this particular problem, it's not explicitly given out, but you could look up, or you conceivably would, if you're doing this as a homework problem, you would be able to look up the vapor pressure of water at pretty much any temperature. There's any temperature given, we know what the vapor pressure of water is, right? So in this system, you have the total pressure is equal to the partial pressure of hydrogen plus the partial pressure of water, which is its vapor pressure. Okay. So at 30 degrees, okay, the vapor pressure of water is 31.86 torr. Okay. You would get this by looking this up. This is in a book. This is probably in your book or in some sort of table. Okay. This is something you'd have to look up. On a test, it's probably something that's given to you. It's not something you would calculate. You'd have to be given this value. But if you're working homework problems, a lot of times the book will assume that you are going and looking this up, right? So if we have 732, well, okay, so it's the same. Torr and millimeters of mercury are the same thing. Right, so if we have 732 millimeters of mercury, this equals partial pressure of hydrogen plus 31.86. Right, so you would just subtract this over, and then we find the partial pressure related to the hydrogen is 700.14 millimeters of mercury, okay, which also corresponds to 0.921 ATM. Okay, so that's what it wanted, or part of it was to find the total pressure or the partial pressure of the hydrogen, which we have. Okay. All right. Now, if we're told here, for the second part, if the total volume is 722 milliliters, what is the mass of hydrogen collected? Okay, so again, here, this is a PV equals nRT problem. Okay, so right, so we're really trying to get this so we can find the grams. Okay, with the molecular weight, we can find the grams. So my partial pressure of my hydrogen, the volume we're told is 722 milliliters, or 0.722 liters. We don't know the moles of hydrogen, that's what we're looking for. R is a gas constant, we have that value. And this was at 30 degrees C, so this is 303 Kelvin. Right, so this is my 30 degrees C plus 273, right? So solving for the moles, okay, just multiply and divide, multiply, and then divide these things over. Okay, we know the moles. About 2 grams per mole. So we get 0.05 grams of hydrogen collected. Okay, so it takes a few of these problems to so we have to do a few of these so we can begin to, because there's a lot of equations. So it's really just a matter of recognizing when or what equations we need to be able to use in order to do these problems. For me, I generally give my students the equations because a lot of these tend to be very plug and chug, but that's not how every professor does. So if we have equations memorized, again, a lot of these you can do with the ideal gas law. You can just keep hammering away with the ideal gas law and solving things that way. It is possible to do pretty much all of these with the ideal gas law, since most of these are just derivations of the ideal gas law. So, all right. So that is it for our practice problems dealing with partial pressure for our gas chapter.